All right, so what we're looking for here is the derivative of our inverse at a. So right here. So if you remember, if you have a function right here, and we plug that a in, what it does is give us the slope of the tangent at that point. So our delta y over delta x. So normally you would just take the derivative, plug in a, there's your slope. The difference is we're not going to have the inverse function here. What we're going to be given is the function itself. So we want a quick way to go from here and its derivative to here. Well, if you look at it, there is the slope of our tangent here, and that's delta x over delta y, with that one being delta y over delta x. So all they are is the inverse. And what also changes is the input. So if you remember, we plug b into our function, we get a. Then when you're plugging a into the inverse to get b. So if we're looking for the inverse at a, then all we have to do is find the inverse of our main function at b, and then just flip it. That's it. So that's what our formula is. It's giving us this, which is really complicated to me, so I just like writing it this way. So if you want the inverse of our, you want the derivative of our inverse function at a, then all you have to do is take and plug the matching y coordinate into b and flip it, and that'll give us our inverse. So let's try one. So I'll let you read it real quick. Give yourself a few seconds. Okay, so f of 4 is equal to 2, and f prime of 4 is 1/4. Then find the derivative of the inverse at 2. So what we want to do first is set it up with our x and y. So we already know that for a function f, what we have is 4, 2, which means our inverse would give us that point at 2, 4. And so you can see there is our correlation there that we want. So if we took the derivative of this function, plugged in 2, which is our x-coordinate, it would give us the slope of this tangent, but we're using this one here. So we know at 4, our f prime of 4 is equal to 1/4, which means if we take our inverse and the derivative and we plug in the y-coordinate of our function, it will give us the reciprocal, flipping it. So that means that our inverse derivative at 2 is 4. Okay, let's try one. So we have our function here, and we're going to be looking for the derivative of the inverse at a. So let's set this up to get a kind of an idea of what's going on here. So our a here is what we're plugging into the inverse. What that means is it's our x-coordinate for our inverse. So it's the y-coordinate for our function f. So now to start this, we want to make sure our function itself is 1-to-1. So it actually has an inverse, right? If it's not 1-to-1, then we're going to have to either modify it to make it 1-to-1, or we can't do this. So is the function 1-to-1? So we look at the derivative and the graph just to verify it. So let's first find its derivative. So if we take the derivative, we get 6x squared plus 8x plus 6. We're going to have to do this anyways, because we're going to have to find a b and plug it in the derivative. So it's a good thing to do. Well, what happens here is this is greater than 0. And the way you can tell it, it's a parabola. And if you look at the graph of the parabola, it's going to give us something that's above 0, which means this is always increasing. And so if it's always increasing, and you can look at the graph, this is the graph of the 3x cubed, our original function. Our graph is always increasing. So if it's always increasing, this isn't going to happen. So we don't have to worry about it coming back down and repeating values. We can do that horizontal line test to show that our function is 1-to-1. So let's look at it with Desmos. This is our derivative. And so you can see our derivative is always above 0, making it greater than 0. So there's our function. And you can see that function, because the derivative is always positive, it will always increase. So going from left to right, our function increases always. So if it always increases, derivative is positive, it's 1-to-1. So if your derivative is always positive or always negative, we know it's 1-to-1 if it's a function itself. All right, so now let's find b. So to find b, we know that that is the y-coordinate. So you can see that here. This is our y for f. So if we set the f of x equal to 5, then we can find our x. Now, we don't have to think here and go, oh, there's 3 solutions to this. We already know that it's 1-to-1. It's not coming back down. So for that y coordinate, we're only going to get one x value. So you can just look at the problem itself and see what it is. And so if we were to plug in 0, you would see that we get 5. So we know that our x value would be 0, giving us the point 0, 5. So if we know that's 0, guess what? That's 0. Right? So we know our b coordinate or our y coordinate for our inverse, and we know our x coordinate for our function itself. So now let's find f prime of b, and this is our b. Okay, so we now take that 0 and we just plug it in. And it's nice 0, so we know it's 6. So again, this is our delta x over delta y. And so our answer is again just flipping it. So for f prime of 5, inverse prime of 5, we get 1, 6. So you can see the relationship here. If I plug the x coordinate for the function in, it gives me 6. And so that y coordinate becomes the x coordinate for the inverse. So plugging that in would give me 1, 6. And that's my answer. So that's how they're related. So if you know the derivative of your one-to-one function, you're also going to know the derivative of the inverse. It's just the reciprocal by plugging in the y coordinate. Okay, there's one little mistake here, though, that we're not noticing. I didn't notice anyways. 3 times 3 is 9, not 6. It doesn't actually affect our answer, but we really should change it just to make sure it's correct. You can see if I plug in 0, it would have zeroed out anyways. That should be a 9, and that should be a 9. Just fix them, and now we're good.